The black hole cosmology idea. To see why the edge looks like a horizon, we need a different map. Start with the core claim. Our observable universe could be the interior of a black hole that formed in a larger, older cosmos, not metaphorically, geometrically. In that picture, what we call our edge isn't a wall sitting out at some distance. It's a causal boundary, the same kind of one-way surface that defines a black hole. Inside it, time and space trade roles in strange ways. Densities soar near the beginning, and yet, to observers like us drifting with the cosmic flow, slices of space can look remarkably flat. Map the pieces carefully. The event horizon in the parent cosmos becomes the limit beyond which signals in here can't be influenced by anything out there. Our observable limit behaves like that. Beyond a certain distance, even light launched now will never reach us. The singular core, the place general relativity says curvature becomes infinite, corresponds to our earliest, highest density epoch. We're not replacing the Big Bang successes, we're reframing the geometry that delivers them. This idea didn't appear from nowhere. Bits of it trail through decades of work. The holographic principle, sharpened by Raphael Bauso and others, insists that in gravitational systems the information content scales with area, not volume. Black holes taught us this with the Bekenstein-Hawking entropy formula. If boundaries count more than guts, a universe with a horizon starts to look like a boundary-driven information system. Meanwhile, proposals from people like Paul Steinhardt's Critics and Alternatives and Lee Smolin's Cosmological Natural Selection flirted with a related picture. Black holes might bud off new universes with slightly varied constants. That's a selection story, not a proof, but it puts the nursery in the right place. There's another thread. Gravitational collapse generically forms horizons, and the interior metric of realistic black holes, rotating, charged, embedded in an expanding background, contains regions where space-like slices admit near-flat geometries. You don't need a miracle, you need the right foliation. In other words, what looks precariously tuned in a free-floating early universe can look typical on the inside of a horizon. The flatness puzzle loses its sting when flat-looking slices are a natural choice for comoving observers. Here, that's what nobody knew at the time inflation took center stage. The price you pay for adding a new field and a new epoch is fine-tuning of a different sort. The black hole interior view shifts the burden to causality. If the edge is an event horizon, then the uniformity across the cosmic microwave background can emerge from data set on a boundary that already correlates the interior. You don't need opposite sides of the sky to shake hands. You need them to inherit conditions from the same surface. But there was one problem. People worry about the word singularity. If we're inside a black hole, do we hit a crunch? Several approaches, loop quantum cosmology bounces, non-singular interior models, ekpyrotic-like compressions, propose that quantum gravity smooths the would-be singularity into a bounce or a finite density start. That's not established fact, it's an active area. The point for our story is narrower. The black hole interior supplies the right stage for high density, a horizon, and correlated initial data without demanding a cosmic coin toss. Let's be precise about stakes. If this reinterpretation holds water, the edge of our universe isn't a distance we'll reach with bigger rockets. It's a causal barrier written into spacetime. Some galaxies are not merely far, they're fundamentally inaccessible. Meanwhile, features that looked coincidental in the standard view become fingerprints of interior geometry. Flatness, uniformity, even certain large-angle anomalies in the microwave sky, all start to look like boundary effects rather than ad hoc patches. Key thinkers scattered along this path help anchor us. Bauso's covariant entropy bound frames what information a horizon can hold. Smolin's cosmic natural selection offers a speculative mechanism. Universes born from black holes inherit parameters, with those producing more black holes becoming more common. Others have explored interior slicings of Schwarzschild and Kerr geometries and their relation to cosmological metrics. None of these alone proves we live inside a black hole. Together, they sketch a blueprint that reinterprets, rather than rejects, our measurements. A natural worry is whether we're swapping one untestable story for another. But this isn't a shrug. It makes contact with numbers. Interior horizons imply specific causal structures. Boundary-driven initial conditions constrain the pattern of fluctuations. Horizon thermodynamics hints that cosmic acceleration could be an emergent pressure from degrees of freedom living on a boundary, not a mysterious fluid in the bulk. We'll stress test all of that against supernovae, baryon acoustic oscillations, and the microwave background, because any viable picture has to pass the same gauntlet as lambdictum. For now, hold the map in your head. Event horizon as observable limit, early high density as interior core, flat-looking slices as a natural foliation for comoving observers. If that's the geometry, then flatness is more than plausible, it's expected. And if the boundary correlates the interior, uniformity stops needing a meeting that never happened. Numbers are about to start cornering us. Flatness is just the first nudge. Uniformity is the gut punch. Fingerprint 1. Flatness without a miracle. This is where numbers start to pin us to the wall. Cosmologists wrap it in symbols, but the itch is simple. Space today looks almost perfectly flat. That means triangles add to 180 degrees on the largest scales. Light rays travel as if the cosmic fabric is uncurved, and the parameter we call omega total hovers painfully close to 1. In the standard framing, that's not neutral. It's unstable. Any tiny early curvature should have amplified over time, tipping the whole universe toward rapid recollapse or runaway openness. To land this close to flat now, the initial value had to be set absurdly close to perfect. On a whiteboard, it shows up inside the Friedmann equation. The expansion rate squared tracks what's in the universe: matter, radiation, dark energy, and a curvature term that's divided by the scale factor squared. Roll the clock back, and that curvature term tries to dominate unless it was nearly zero to start. In practice, it means at a fraction of a second after the Big Bang, the deviation from flatness had to be 1 part in many trillions. If that sounds like balancing a pencil on its tip in an earthquake, that's how it feels. Inflation came in as the elegant fix. Stretch space by an enormous factor, and any initial curvature gets ironed flat. The same trick smooths out in homogeneities, and with quantum jitters frozen in and stretched, seeds a nearly scale-invariant spectrum of ripples. But now you've traded one question for another. What set up the inflattened field, the shape of its potential, and the exact conditions that let it start, run long enough, and end gracefully? The pencil is no longer balancing after 1 second. It's balancing on the layout of a field you can't see, with parameters you choose to make the math behave. Here's the twist the black hole interior view brings. Inside a horizon, the way you slice spacetime matters. For observers who drift with the interior flow, there are natural choices of spatial slices that look flat even though the full geometry is wildly curved. In the interior of a Schwarzschild or Kerr black hole, certain constant-time surfaces that comoving observers would call space right now can be foliated to appear spatially flat to those observers, because the strong curvature is encoded in how those slices evolve, not in their instantaneous shape. That's more than a mathematical parlor trick. It means that near flatness on the slices we sample, our cosmic time surfaces, needn't be a fragile miracle. It can be a built-in feature of living inside a horizon. The curvature is real, but it's packed into the time direction and into the causal structure, not into the three-dimensional geometry we measure at a fixed cosmic time. What looked like a precarious dial setting in a freestanding early universe becomes a natural perspective effect of interior geometry. A small group met to puzzle this out in a cramped office, windows fogged by winter breath. One of them drew the usual FLRW line, another layered in interior coordinates from a black hole metric. The room got quiet when the flat foliation dropped out with no finger-on-the-scale assumptions. Someone said, "If the slices we live on want to be flat in here, Maybe we've been worrying about the wrong miracle. The board filled with arrows. Inside horizon implies foliation freedom, implies observational near flatness without tuning. Pause on stakes. This is not a free pass to ignore data. We still measure curvature through the sum of omega values using the microwave background's acoustic peaks, baryon acoustic oscillations, and lensing. Those numbers keep saying flat within small errors. In the inflation picture, that's a win because stretching kills curvature. In the black hole interior picture, it's a win because our observational slices naturally come out flat-like. Two roads, same signpost. The power here is that one road removes the need for a delicate starting point. There's a second payoff. The fine-tuning moves from initial conditions to geometry. We aren't begging the universe to begin almost perfectly flat. We're recognizing that for moving observers inside a horizon, flatness is an emergent property of how you cut the spacetime. That makes flatness less of a coincidence and more of a diagnostic. If we saw strong, persistent curvature today, this interior picture would be in trouble. Seeing near flatness again and again is the nudge. Of course, the skeptic in the room raises a hand. Can an interior that's curved in 4 dimensions really hide spatial curvature from us? The answer is yes, and we already live with echoes of that idea. Think of de Sitter spacetime. You can write it with different coordinate choices, some that make space look flat, some closed, some open, all describing the same physical world. Geometry's story changes with slicing, but observables don't. The black hole interior adds a causal horizon that picks out which slices are physically relevant to us. This doesn't prove the case, it sharpens it. Flatness, once an argument for a rapid stretching episode, also fits an interior horizon where our clocks and rulers sit on flat-like slices by construction. We don't have to invoke a special roll of the cosmic dice. We have to take horizons seriously. And if flatness is just the first nudge, uniformity is the gut punch waiting on the other side of the board. Fingerprint 2, the horizon problem recast. Stand on a mountaintop at night and look east and west. The microwave glow you're seeing from both directions has the same temperature to 1 part in 100,000. In the standard story, those 2 patches never had time to talk before that light was released. No messages, no heat exchange, no shared past light cone. Yet they match like synchronized clocks. That's the horizon problem. Distant regions of the early universe look coordinated without causal contact. To feel it in your bones, we need 2 horizons on the table. The particle horizon tells you how far light could have traveled since the beginning until a given time, who could have ever talked to whom. The event horizon is about the opposite, the boundary beyond which signals, even if sent now and forever, never reach you. In the textbook Big Bang Without Inflation, the microwave sky's opposite points lie beyond each other's particle horizons at recombination. They shouldn't have equilibrated. Inflation fixes this by pushing tiny, well-mixed regions to cosmic scales, so patches we see far apart were once neighbors. The black hole interior view doesn't deny the geometry of light cones. It reframes the causal bookkeeping. Inside a horizon, causality compresses in a different way. Data that sets the interior's initial state can live on the boundary itself. If the edge of our cosmos is an event horizon in apparent spacetime, then much of what we call initial conditions is inherited from a single surface that already correlates the entire interior. You don't need opposite sides of the primordial plasma to exchange photons. You need them to be born from the same boundary prescription. Here, S where horizon crossing flips roles. In inflation, fluctuations start inside the Hubble radius, exit during rapid expansion, then re-enter later to seed galaxies. In a collapsing parent region that forms a black hole, modes can be driven the other way. Compression pushes wavelengths across an interior horizon, freezing correlations set by boundary conditions. When the interior later expands along its own time direction, those imprinted correlations ride the flow. The matching temperature across the microwave sky isn't a conspiracy, it's the echo of shared origin data. Boundary rule. That note on a grad student's printout wasn't a throwaway. Holography argues that the maximum information in a region scales with its bounding area. If that's the bookkeeper, then the early interior's degrees of freedom are not free to wander uncoordinated. They're constrained by a global ledger written on the horizon. From our perspective, that shows up as uniformity with slight, structured deviations, exactly the pattern we observe, a near-perfect blackbody with small anisotropies. Let's be concrete about signals. Picture light cones painted onto a spacetime diagram of an interior region. The past light cone of a point on the last scattering surface doesn't intersect the past light cone of a point on the opposite side, if you only consider bulk propagation. But if the state of that entire slice was fixed by boundary data laid down when the horizon formed, then those 2 points share ancestry through the boundary, not direct bulk conversation. It's a different way of threading causality. The bulk inherits, then evolves. There's an extra mechanism hiding in plain sight. Near a horizon, the redshifting and blueshifting of modes depend on surface gravity, a measure of the horizon's acceleration. If the parent horizon's properties set a temperature and a spectrum of fluctuations, then the interior gets a template for the variations we later measure. That's not a claim that Hawking radiation painted the CMB. It's a statement about boundary-imposed initial power. The spectrum we see could be a projection of horizon-encoded correlations. Meanwhile, in a dim control room, a CMB analyst stares at a sky map after another round of calibration has wiped out instrument quirks. The map is still too smooth. The tiny hot and cold spots are there, but the large-scale modes feel eerily quiet. Low power at the largest angles. Odd alignments that statisticians argue over. She rubs her eyes. If the early plasma obeyed simple bulk causality alone, why do the biggest patterns look like someone gently pressed flat? She writes edge imprint in the margin and circles it twice. Skeptics jump in quickly. Uniformity from a boundary sounds like magic unless you show the math. Fair. The math lives in how you set initial conditions for fields in a spacetime with a horizon. Holographic ideas like Balso's covariant entropy bound constrain what can be stored and how it's distributed. In practice, that means the interior's quantum fields can start in correlated states that respect the boundary's limited information capacity. When those fields couple to photons and baryons, the result is a plasma whose temperature is astonishingly even, before any bulk equilibration. There's a crucial difference in tone here. Inflation is a dynamical cure. It does work to smooth and stretch. The interior horizon view is a kinematic cure. It limits what initial states are allowed and correlates them at birth. Both can generate a nearly scale-invariant spectrum with small deviations. Both concede the acoustic peaks we later measure. The payoff for the interior story is economy. You get uniformity without a separate era that needs finely chosen potentials and exit strategies. Importantly, this recast horizon story is falsifiable in spirit. If future maps found strong, unambiguous signatures of regions that never shared boundary ancestry, clear, inconsistent patches that demand local, late-time equilibration, we'd be in trouble. Instead, the sky keeps whispering one message: uniform with structured global correlations. The boundary did the talking, and the echo of that talk is still cooling through us. The holographic playbook. If the boundary did the talking, we need to learn its language. Start with a rule that black holes forced on us: information scales with area, not volume.